Well, good evening, everyone, and thank you for joining the AIPG Texas webinar series. I wanted to just quickly note that tomorrow we will be holding the AIPG Student ECP webinar series. We're launching that tomorrow, and it's going to be, we're going to be talking about licensures and certifications. And then also just a reminder, next Tuesday, we will be doing our Lunch and Earn. And so next Tuesday's topic is planning for a drill campaign. So be sure to sign up for those as well. And tonight we want to welcome Lorena, Dr. Lorena Moscardelli, who's going to be giving our presentation tonight. So Lorena, if you want to give a brief kind of description of yourself, that would really be great. Thank you so much.
Sure. Well, first, thank you for the invitation. I'm very honored to be here with you guys. Essentially what I'm going to do today is I would like to talk about the STARR program at BEG, a brief introduction about the program, and then I'm going to dive a little bit deeper on a particular project that we are leading right now on hydrogen storage. Before we go there, STARR is the State of Texas Advanced Resource Recovery Program. I'm the principal investigator of this program, and hopefully, as I mentioned, I will be able to provide today some sort of a glimpse in terms of the exciting activities that are keeping us busy. A little bit about me. I'm a Venezuelan-American geoscientist. I started my career as an exploration geologist in PDVSA, and then I came to Texas to get my PhD, and after graduation, I started to work at the Bureau as a researcher. I did that in a different research group for 6 years, and then I started to work for Statoil, now Equinor, first on the research center here in Austin, and then I had done work for exploration and field development, mostly in Norwegian continental shelf in Norway and offshore Canada and so on. 2 years ago, I decided to come back home to Texas, and now I'm holding this position as leader of the STARR program. So with that, let's see if this is working. This is a little bit of an outline. This first part is going to be around, 10-15 minutes. I will introduce the updated STARR mission. We will talk about something that I'm calling now STARR Energy. You will see that this is a big program, so I'll concentrate on the STARR Energy component. I'll briefly introduce the STARR team. I will talk about the STARR operating model by showcasing some examples of ongoing projects and initiatives. I'm not going to dive too deep on all of these initiatives, but I want to make you aware of the kind of work that my team does. And finally, I will talk a little bit about STARR and what we're doing in terms of this whole thing associated with the energy transition, emphasizing our current initiatives on hydrogen storage, which I find very interesting. So the STARR mission is to conduct geoscience and engineering research to increase the production and profitability of Earth resources, including oil, natural gas, hydrogen, geothermal, and minerals, within the state of Texas, while encouraging responsible economic development and supporting education and environmental stewardship. We do this by funding a variety of initiatives in close collaboration with other BEG groups and tackling a wide variety of topics that are of high relevance for the state. And this includes water resources, mineral and earth resources, energy. I will talk mostly about this box here, land resources, geohazards, and we also have special projects. This is the STARR energy structure, essentially how this box looks like. We have the G&G component that is broken up into the regional initiatives covering broader stratigraphic and geographic areas across the state, and that feed from our one-on-one interactions with Texas operators. This is how we define our research priorities, talking to the operators here in Texas. The program also has an engineering component that focuses on improved oil recovery strategies and some hydrogen initiatives. And finally, we have special projects with an ongoing hydrogen storage and on salt domes or salt formations, both in the Gulf Coast and West Texas. The idea here is to tackle specific technical initiatives without losing the broader vision of multidisciplinary collaboration. We also want to have flexibility to engage with emerging opportunities like broader BEG hydrogen initiative. And I mentioned earlier that we collaborate with other groups. So BEG has a group called GOH2, and we collaborate with them in the hydrogen part of things. This is part of the team. Actually, this slide is not up to date, but we have an impressive combination of experience levels from early career researchers to senior research scientists who advise me and the team, in addition to engaging with the specific research projects. So I really lean heavily on the experience of our senior research scientists. We also have a wide range of expertise, including engineers, geologists, geophysicists, geochemists, and GIS specialists. But the most impressive thing for me is the wide range of scales of observations that our researchers can handle, from the micro scale to the regional. These guys do a whole lot of things. They can code their own way to applications and build subsurface models. We also have students and postdocs that add great value to the program. So a lot of activity, So the pillars of how we operate are sustained by four basic modalities. One is the direct collaboration with Texas operators. This engagement is our main thermometer on how we define research priorities. They bring the problems to us, and we design projects to offer solutions in a partnership model. We cannot say yes to everything, but we do our best to pick the best projects and so on. Once we identify those hot topics based on these one-on-one interactions that I was mentioning, we define the focus of the regional initiatives that usually end up as peer review publications or reports of investigations, workshops. So these are our long-term deliverables. And at the end of the day, we are a research institution. So part of our mandate is to generate knowledge, right? So we need to publish. Then the G&G part of things is a fundamental component of a STARR, but the engineering engagement to offer solutions regarding a variety of things, from stranded oil and strategies to increase production, from, right now we have a hydrogen storage and cycling app that one of our engineers coded. I mean, we also engage, what I'm trying to say, we also engage in engineering solutions that feed from our G&G knowledge, right? Finally, it's important for us to have flexibility to engage in alternative lines of research, especially now that things are kind of evolving, and the hydrogen storage and geothermal components are part of this flexibility. So this is key, something that I consider key to balance our portfolio of projects that might look different now from 5, 10, 15 years from now. Regarding membership, no cost associated with participation in the STARR program, which is funded by the state of Texas. However, matching support and willingness to facilitate publication of research results and data, it's important for us. And since we are in really high demand, we need to be selective sometimes with our projects. We cannot say yes to everything, because even though we're a big group, we have some limitations. So, okay, so these are 3 examples of ongoing one-on-one collaborations with Texas operators. The first one is led by Bill Ambrose. It is a FRIO characterization study that includes well correlations, the positional environment interpretation, and production matching. The aim here was to identify potential prospective intervals that have not been targeted yet by the operator, but this work is ending up as a report of investigation because then we can zoom out and kind of do more of a regional trend and talk about the geology and the research component. The second example is led by one of our early career researchers, Lucy Ko. This project is on the Barnett, unconventional play. It's a very fascinating project, and this is in partnership with the BKV Corporation, an entity that acquired Devon's Barnett position not long ago, I guess, becoming an important player in this region. And they're interested in using BEG's existing knowledge to catch up with the subsurface characterization component of their acreage, as well as to engage in the research by sharing new data, including seismic, hopefully at some point in the future. And they also have voiced interest in CCUS opportunities. So then finally, on this slide, I have the Lower Permian Tiny Hill Sandstone study that is led by one of our geophysicists, Chris Ogisowa, in partnership with Burnett Oil. The study seeks to use seismic inversion to refine the areal distribution of sandstone intervals and better understand the shelf margin architecture of the early Permian. Okay, so those are examples more of like one-on-one interactions with operators, mature, I would call them mature interactions with them with very well-defined projects. But then usually we take that one-on-one to go into the next level, you know, that is a different scale, it's regional, okay? So here I'm showcasing two examples of regional studies that our team has been pursuing, that, as I mentioned, fed into these initial one-on-one interactions with operators. To the left, an effort by Kelly Hattori on the Lower Cretaceous Pettet Formation in northeastern Texas. There has been hydrocarbon production from oolitic shoals of the Pettet Formation, but to date, you know, very little has been published on the variability of these oolitic shoals that could help predict reservoir presence and quality within this underexplored unit. So Kelly's currently working on a manuscript on this topic where she's matching some of these trends also with production and so on. And we are planning to engage with some modeling in the future to try to understand how these oolitic shoals are actually controlled by underlying salt formations or salt domes. To the right, work by one of our PhD students, Fritz Palacios. Fritz is updating the stratigraphic framework of the Eastern Shelf Midland Basin. Although this succession has been extensively studied over a century, recent advances in biostratigraphy, along with modern wireline logs and 3D seismic data, allow for the revision of some of these stratigraphic models to generate new play concepts. So I have to say operators are very interested in this work by Fritz. He's right now mostly concentrating on the Cisco group. I'm very interested in this mixed siliciclastic carbonate system. And yeah, we are actively working on this. So I'm hoping that Fritz will be able to graduate this year. And this also speaks to our educational mission, right? As I mentioned, the STARR program also has a strong reservoir engineering component that relies on data integration from multiple subdisciplines. And here I'm showing just one of these studies. The Seminole study led by Ian Duncan is a very good example. This study focuses on the Seminole San Andreas unit in the Central Basin platform of the Permian Basin. The residual oil zone consists of carbonates with anhydride intercalations within a carbonate ramp setting in the San Andreas Formation. And this work included, machine learning analysis of water and log data, petrophysical measurements of porosity, permeability, and capillary pressure. Isotopic analysis and so on. Actually, we recently hired a new postdoc who will be working on this also with Ian and Robin Dominis. But some of the conclusions here are suggesting from their work that heterogeneities in the flow properties strongly influence the performance for both oil production from CO2 injection and potential associated CO2 storage. You can sense here that these research capabilities in terms of data integration and modeling are important now, but will continue to be important in the future. So we continue to put some resources on, or put considerable amount of resources into this. Right, so now I'm kind of shifting a little bit into the energy transition component of things. So regarding STARR special projects, we are currently pursuing a scoping project that seeks to evaluate the feasibility of hydrogen storage in soil caverns. This illustration to the left shows potential hydrogen storage solutions that include salt domes, but also depleted hydrocarbon reservoirs, aquifers, and so on. But from these three options, salt caverns are the proven concept. However, upscaling the hydrogen storage in salt caverns, given the amount of hydrogen that we're going to need, it will require additional research. It's not a trivial exercise, There are 3 hydrogen storage facilities in underground salt caverns in Texas. I'm showing them here in these kind of yellow stars around the Houston area. So the map shows, also a GIS effort that seeks to visualize and put together this kind of catalog of salt domes in the Gulf Coast, which essentially here are the red dots. They also shows salt caverns on the diamonds with different uses and some infrastructure associated with CO2 pipelines, hydrogen pipelines, natural gas pipelines, and so on. So I think what I need to do now is I would like to switch my presentation. Let's see if I can do this. And I'm hoping that you can still see my screen, correct? Hello? Can you hear me, guys?
Yes, we can hear you.
Okay, perfect. And you can see my screen too, right?
Yes, we can.
Which one are you seeing? Are you seeing, wait.
It says transition to H2 presentation.
You're still on that one. Wait, let me just stop the sharing for a second. And let me see here. So I'm gonna share again. And now what are you seeing?
Now we see the hydrogen economy and subsurface storage real estate.
But not the notes. You see the proper.
Yes, in presentation mode.
In
yes.
Presentation mode. Okay, so then let me just minimize this. Okay, so I hopefully have been able to give you an overall vision of what the STARR team does, and I would like to dig a little bit deeper into this hydrogen storage research component. And yeah, I'm going to skip this. We already talked about this. But, without spending too much time on this, one of the things is that lately we have been hearing about, the impact that CO2 emissions can have on climate change and global warming and so on. But regardless of our position on the matter, the reality is that, a lot of companies, especially majors, are investing a lot of capital into this energy transition stuff. And we're starting to see activity also here in the US and in Texas. So for a while, as probably most of us, I have been wondering, what's the role of geoscientists and engineers working in oil and gas industry as part of this transition. And I have come to the conclusion that we're not only talking about oil and gas, even though that will continue to be an important component of the energy mix for many, many years. But we're talking about energy, right? A broader concept of energy. So that transition it's a process that will take a period that hopefully, will change from one state to another. But this has been happening since we were burning wood to burning natural gas, So oil and gas will still play an important role, and many other technical challenges are arising. And I think this is a good thing, especially from the research side, because it's like, okay, how do we sort this out? It's interesting when you look at these things. I think it's better for us to see the destination we wish to reach than the point of departure. But there is still a lot of work to do. So here it comes hydrogen, as an alternative to help us in this transition. And as I was mentioning earlier, a lot of companies are investing both in Europe and also here in the US now on these projects. So hydrogen can be used as an energy carrier, allowing the transportation and storage of energy. And this is the storage component where I'm going to finally land. Some facts about hydrogen is the lightest element in the periodic table. It's colorless, odorless, non-toxic, highly combustible, non-metallic. It is the most abundant chemical substance in the universe. But most of the hydrogen on Earth exists in molecular forms such as water and organic compounds as methane. And this is the important part. We cannot just grab hydrogen, from a reservoir, even though there are some naturally occurring seeps of hydrogen. But volumetrically speaking, that's not enough. Where does it make sense to use hydrogen? Well, especially for hard-to-abate industries where you actually need actual molecules to burn, to run processes. We're talking about cement and steel, also for transportation, but long-distance transportation, like big ships or maybe trucking and things like that. That's where hydrogen has more sense to use. You will hear that people talk about colors, blue hydrogen, white hydrogen, and so on. It gets to a point that it's very confusing, in my opinion. So I essentially use three colors. So green hydrogen is the one that is derived by breaking up the water molecule, by using renewable energy. But that's very expensive right now. Essentially, electrolyzers are super expensive, and then you need a lot of clean water, which is not that easy to get, especially in places like West Texas, right? Then we have blue hydrogen, which I think is more realistic to kickstart this. And blue hydrogen, essentially what it is, you take natural gas, right? You take the methane molecule, you use steam methane reforming or thermal methane reforming, and you break the methane molecule into hydrogen. and you have a byproduct, right? You have CO2. So that CO2 you capture and then you sequester on the subsurface. And then you have gray hydrogen, that is the hydrogen that we produce today. And essentially it's the same method that I just described with blue hydrogen, but the CO2 is released to the atmosphere. And then you also have, brown or black hydrogen, where instead of using natural gas, you use coal and coal gasification and other things. A lot of hydrogen is made like that in that way in China, for example. So how, especially for the green hydrogen component, and remember, green hydrogen is the hydrogen derived from breaking up the water molecule using renewable energy. Why does that play a role, and what's the link with storage? I really like this tornado plot because it shows you the cost of intermittency and curtailment of wind energy in the UK from 2012 to 2030. Okay, so this is the wind energy curtailment in terawatt hours versus the cost of that. And essentially what this is it is true that the wind doesn't always blow, but sometimes it blows a lot, especially in certain coastal areas. And when you're generating more energy, renewable energy than you are consuming or you can transport to market, there is a waste in there. And that waste has a cost, because the things that you need to do in terms of infrastructure and the facilities and so on, there is a cost associated with that. So in 2020, the UK government had to pay around £274 million because 3.7 terawatt hours of this renewable energy associated with wind was curtailed. So there is a cost to this waste. So the logic in terms of hydrogen storage in this particular case, what if we can take these 3.7 terawatt hours of energy or excess energy and use that to feed our electrolyzers to generate hydrogen that then we store in a salt cavern, for example. And then, during the winter or during times when the wind is not blowing, we can then take that hydrogen and we can generate electricity or use it for industrial processes or so on. So that's the logic behind, hydrogen storage and renewables. So I see hydrogen storage in geological formations as some sort of a mega battery, And I like this plot because it's showing you in the x-axis power from kilowatt to gigawatt in here, the scale, and then the discharge time in the y-axis from seconds to days. So regular batteries, are can deliver, from kilowatt to megawatt hours in a matter of hours, and there is a place for this kind of technology, But when we're talking about gigawatt scale, and we're talking about days or weeks or months of need for discharge, we're talking about bulk power management. And here is where geological storage plays an important role. This is not a new concept. Actually, we do it with natural gas, right? So I showed you this in a previous slide. Let me see how we're doing in time here. So there are currently hydrogen storage facilities. There are 4 locations around the world where we have salt caverns where we store hydrogen. 3 of them are along the Gulf Coast, okay? Clemens Dome, Moss Bluff, and Spindletop. And 1 is embedded salt formations in Teesside in the UK. The important thing about this is to mention that this hydrogen storage is mainly used as a strategic storage. This hydrogen is used for refineries that use the hydrogen to remove sulfur from hydrocarbons, and also used by the petrochemical industry mainly. So the idea of having this hydrogen stored in there is that if there is, issue with the hydrogen supply in the refinery, for instance, you don't have to shut down the refinery. You can go to your storage. And these facilities have been working for decades in there. But the important bit in here is that people oftentimes talk about hydrogen storage as a proven technology. It is and it isn't, because it has never been used for power generation, And this is important because when we're talking about hydrogen in this context, then we're talking about high frequency injection withdrawal cycles. Right now, even though it's very difficult to find data from these operators, they probably tap into these salt caverns, I don't know, once a year, or once every 5 years or so on. Or when we're talking about within the context of the energy transition, we're talking about high frequency injection withdrawal cycles, which poses a huge challenge from an engineering perspective, okay? So that's what we are trying to understand, and that's what we are studying. So these salt caverns, how do they look like? Well, think about a typical salt dome along the Gulf Coast, maybe 3 miles high, 2 miles in diameter. I'm just giving here bulk numbers. One of these caverns can be around 200 feet in diameter and around 2,000 feet high. And one single dome can have multiple salt caverns in them. Now, this is a nice cartoon. Everything is homogeneous and so on, but what we're finding out, or what we know already, is that even in onshore salt domes, these salt domes are not that homogeneous. There is a lot of heterogeneity that you can find inside these salt bodies. And in fact, we know that in some of these hydrogen storage facilities, sometimes they inject their hydrogen and they have contamination by methane. So where is this methane coming from? So we think part of it is migration through intrasalt deformation that somehow connects with the mini basins. These are active petroleum systems, and you have some kind of communication to your cavern, which is something that you don't want, right? So we're trying to understand how that works. Salt caverns have been around for a long time. This is not new, and they have been used for a variety of things, including waste disposal from oil and gas operations, oil and gas storage, salt mining by solution mining, and so on. Probably the most famous, user of salt caverns is the Strategic Petroleum Reserve. So there are 4 locations along the Gulf Coast where the SPR has around 60 salt caverns with an average diameter of 2,000 feet and a height of around 2,500 feet, where they store, liquid hydrocarbons. And this is just giving you a plan view of one of these salt domes. And in green, you see the multiple salt caverns. Okay, so in one salt dome you can have even, I don't know, tens of them. And this is how a salt dome looks like in onshore seismic. It's not as pretty as the seismic offshore, but it gives you an idea of how they look like. There are different types of salt, and these are graphs from a publication in the Solution Mining Research Institute, I believe, that shows you the distribution of both domal salt and bedded salt. The constraint with domal salt, or salt formations in general, they are geographically constrained. In particular, salt domes are more constrained in terms of geographic location. Like, for instance, in the US, is only along the Gulf Coast. But we also have bedded salt formations that would offer a broader opportunity to place these salt caverns in different geographic locations. And so both options are possible. So one of the things that we are trying to do, as I mentioned, is to map where our salt domes are located, where our hydrogen pipelines are, where our CO2 pipelines are, because, I mean, when we're talking about this also, this is one of those elements where you need co-location of surface and subsurface resources, right? You want to identify the salt domes that are closer to steam methane reformers, for instance, that are closer to areas where you have higher potential of hydrogen generation by renewables, places that are closer to market. So it's not only the subsurface component of it, it's the entire ecosystem. When we're talking about blue hydrogen, then we're talking about also CO2 sequestration. So you need to have a place to generate your hydrogen, a place to store the hydrogen, and then also a place to permanently sequester the CO2. So going back to my question, or these thoughts of what's the role of the geoscientist on this, I think we have a lot of work to do. One of the things is, well, how to predict weak zones, and this, depending on who you ask, and I'm not a salt tectonic expert, a lot of people talk about spines, making reference to this intrasalt salt deformation component. And sometimes what happens with these caverns is that operators drill into the salt, they leach, by injecting fresh water and producing brine. This is a process, by the way, this is fascinating. It can last 2-3 years to build one of these caverns. And then sometimes they have issues. They have shear zones that deform their casing or deform their caverns and so on. So knowing or planning properly where to place your cavern is an important thing. And here is where, research is important. This is just a numerical model that shows you how a salt diaper can form, and is showing you velocity of the salt. And you can see these differences in velocity that might be related to some of the things that you see in intra-salt deformation that can be linked to the formation of these shear zones or weak zones, right? Also on physical models, you see that the salt doesn't move uniformly. There are heterogeneities inside the salt that can generate these weak zones and so on. So there is a lot that needs to be learned from this. One of the main questions, and this is fascinating, I find this very interesting, things like, what is the origin of methane contamination of stored hydrogen, which we know happen, is this associated with gas inclusions within the salt body that were already there? Is this associated with the presence of shear zones or weak zones or spines or whatever you want to call them that somehow connect the inside and the outside of the salt domes? Questions such as, what are the mitigation measures to avoid or remediate methane contamination? Should we avoid active petroleum systems in surrounding areas, which I don't think is possible? Are there any engineering solutions? So these are things that we are we don't necessarily have answers for this, but things that we're interested in better understanding. I have been talking a lot about salt and salt caverns, but for those of you who are familiar also with natural gas, you know that you can also store natural gas on porous media. That includes, depleted reservoirs or aquifers and so on. And the same concept is applicable in theory to hydrogen, but the challenges here are a whole lot larger. I mean, the benefit of storing hydrogen on porous media is that you don't have to worry about the geographic distribution of salt formations, right? We have porous media in more areas. The other advantage is that volumetrically speaking, you can store more. Yes, even though the injection withdrawal cycles will be slower, you can store more hydrogen. But the problem with this is that hydrogen is very different in terms of its properties to methane, and is very reactive, and diffusive. So things like, if I have hydrogen and I put this hydrogen in contact with pyrite, I'll have H2S. That's one potential reaction. The other thing is that if there are microbes, in the subsurface or the aquifer, they love hydrogen and they will eat the hydrogen, and the hydrogen is expensive. You don't want to lose your hydrogen because microbes are eating the same, right? It's very diffusive, so you can lose your hydrogen just by diffusivity. So how does that work? So there is a very active in terms of research. I think there are more challenges associated with this that with salt caverns. I just wanted to make you aware of that. And this is a great simulation by one of our former engineers. Lorena is showing you the differences in terms of diffusivity between hydrogen and CO2 in an aquifer. So this is CO2. You can see the fingering, but in real time you can compare that with hydrogen, right? So this is a whole lot more diffusive. I think I'm going to skip this one. So some conclusions here. There are more than 80 salt domes in the Texas Gulf Coast that can provide feasible hydrogen storage options in the short term. Many of these domes are close to relevant infrastructure and access to market, ensuring quick monetization while accelerating energy transition goals. Research is needed to better predict optimal positioning of salt caverns and to optimize salt dome, I call it real estate. It's interesting that we have received requests from small operators, that maybe have surface rights and some mineral rights over at home and start to ask, hey, how do I get into this salt cavern situation, So another thing to think about is, potential hydrogen storage in offshore salt domes. Excuse me. And this could play an important role in planning for electrification of, for example, of offshore oil and gas platforms, just an idea. West Texas layer salt formations are also prime targets to evaluate the feasibility of green hydrogen in West Texas. So there are different things that we're doing. We are currently working with one of our engineers, doing some coding to put together this hydrogen storage and cycling app. For me, that's extremely important to understand how this high frequencies cyclicity is going to work and what is the impact, not only on the cavern, but in general on the infrastructure, the techno-economics of how this is going to work, as well, is extremely important. So I think that's my last slide, and I'm gonna just open for questions.
I believe John Berry has joined us now. I'm not sure, John, if you have a couple of comments you want to make. Well, thank you, Dr. Lorena Moscardelli. We really appreciate you presenting tonight for our Texas webinar series. If anybody does have a question, if you want to put it in the chat box, we will take a look at them. And Lorena, can you see the chat box, or would you like me to read them? Okay.
I can see. I'm going to try to go through this. I think Ross has a question. How much methane is allowable in blue hydrogen? Well, blue hydrogen is derived exclusively from methane. So the important thing is really how much CO2. I mean, if you ask the Department of Energy, when we're talking about clean hydrogen production, regardless of source, the definition is linked to the amount of CO2 that you are producing. So in the case of blue hydrogen, the idea is to optimize your steam methane reforming or autothermal reforming process, so that by exact 1 kilogram of hydrogen, I don't remember the numbers right now, but for let's say 1 kilogram of hydrogen produced from methane, you have a CO2 amount that is less than X. I don't remember the X number right now. Yeah. And then that CO2 needs to be captured and sequestered permanently. I don't know if that answers the question. Let's see if we have something else. It's a very shy audience. Yeah, how do you view the competition between water usage and hydrogen storage in Texas? Have regional studies been done on how hydrogen storage could impact areas? Well, that's a concern that I have, because it's not only green hydrogen, the one that is from breaking up the water molecule. Also, blue hydrogen is a problem, because steam methane reforming, you need some steam. So you need I think for blue hydrogen is something like the equivalent of, I don't know, 10 liters of water or 15 liters of water for kilogram of hydrogen that you produce. That's a lot. And then for green hydrogen, I think it's like 9 liters of clean water, because for green hydrogen, the challenge is even worse, because the water needs to be relatively clean, for the electrolyzers, at least the electrolyzers that are in the market today, to be able to process that. So I think as everything in life, there are always technology breakthroughs. Right now it's a challenge, but if you think about West Texas, there is a whole lot of produced water in West Texas, for instance. I think sometimes it can go to 8 barrels of produced water per barrel of oil produced, right? If there are technological breakthroughs that will allow us to use that produced water either for steam methane reforming or electrolysis, then actually it can be a nice ecosystem where we have a problem that is produced water, and we kind of profit from that to make hydrogen. But I don't think we're there yet. What I know is that there is a lot of efforts in particularly in Europe, but also here in the States. The DOE is starting to invest a lot of money on this to try to push forward these technologies. And I think it's going to happen. The question is when it's going to happen. So I think that's the main challenge. But you're correct. Right now is a problem. Jim Lerman, what's the cost of blue hydrogen per BTU compared to natural gas? How can hydrogen become more cost competitive? Well, the short answer to that is that right now it's not competitive compared to natural gas for a variety of reasons. One thing that I didn't show or I didn't comment is that, 1 unit, in order to generate the same amount of energy that we can generate using 1 unit of methane, I think we need like the equivalent of 3 units of hydrogen, and not only that, but I mean, like you can imagine, volumetrically speaking, we need a whole lot of hydrogen to generate the same amount of energy that we generate with methane. And that's also a challenge in terms of storage and storage space. So it's not competitive right now with natural gas. I think the DOE has a target of having by 2030, I think the target is to have the cost of 1 kilogram of hydrogen down to, I think it's $1 or something like that. We're definitely not there, but we have seen that, for instance, I don't know, like 4 or 5 years ago, I think the cost of green hydrogen was around $6 per kilogram, which is a lot. And right now in some areas, estimations indicate that it could go down to $3 or something like that. So you see that this is starting to change. But Jim, I think, yeah, the short answer to that one is that right now it's not competitive. Yeah. And I don't have all the numbers in my head. I made a presentation a couple of weeks ago on this, but yeah, I don't have the numbers here right now. Let's see, any other questions or comments?
No
No,
more questions, it sounds like. And we want to again thank you, Dr. Moscardelli, for presenting tonight. We do really appreciate your time, and we appreciate everyone who is listening as well. If there are no other questions, we will go ahead and close this out, and we hope to see everyone at a future webinar that AIPG is presenting. Thanks again, everyone.
I just want to thank Lorena Moscardelli. This is John Berry speaking, and apologize for not having been here for the beginning of the talk. It's rather unforgivable, and I'm sorry, Lorena. Thank you.
no problem, John. Thank you for the invitation. Always a pleasure, you know. So you know where to find us here in Texas. Bye, everybody.
Thank you.
Bye-bye.
Goodbye.
Bye.